Hi, Chris Good here. Guess what? It's time for another repeated measures analysis of variance problem. This one's number 2. The handout that we've been working on in class here, a therapist is interested on helping individuals with ophidiophobia, fear of snakes. In order to do this, the therapist is going to slowly desensitize the patients to snakes, needs to find a starting point, so he presents a sample of 8 ophidiophobics with snake-related stimuli. It should be hyphenated, snake-related stimuli, and measured their physiological response. Let's say that a bigger number then probably means a greater fear response. Let's assume that that's true. Okay. Just like always, we're going to do some hypothesis testing steps. First, state the null hypothesis. Here, the mu for the picture is equal to the mu for the plastic toy snake, which is equal to the mu for the rubber lifelike toy snake. And just like before, I've taken some steps to shorten this video. I've already calculated the sums of squares for each one. You guys should already know how to do this by now, but we're looking at the sums of squares just for each group. You just sum the squared scores, right, for each one, and I've done that here for this first group, the picture. And you subtract the square of the sum of the scores divided by the number of scores in that group, not big N, the number of all the scores in the group. This is just a regular sum of squares for this distribution of numbers. Same for this one, same for this one. And you can check your work by following along with what I've written here. I've also done the t's for each group. I've done the means for each group. I did the p's in advance too. I'm just going to go ahead and fill those in because we're going to need those in just a second. So that's 33 for the first one, 26, 25. This is just adding the total scores for each participant. 34 for participant number 4, 21, 18, 27, and 26. Okay? There you go. Those are p's. We're going to use that to calculate the sum of squares between subjects. Step 2 is to state your alpha, right? We're going to use 0.05. And f is always just a one-tailed test, but to find f crit, we do need 2 types of degrees of freedom. We're going to need degrees of freedom for the numerator of the f ratio and for the denominator. And the repeated measures f in the numerator has mean squared between what? Not between subjects, between treatments. But the denominator is a little bit different from the independent groups in ANOVA. The denominator is MS error. So we need to find the degrees of freedom for between treatments. That's pretty easy. There's 3 treatments. Degrees of freedom between treatments is k minus 1, or 3 minus 1, or 2. That's easy. Degrees of freedom error are different, so we have to get them by subtraction. We're going to get sum of squares error by subtracting sum of squares within treatments minus sum of squares between subjects, so we're going to get degrees of freedom the same way. So df error is going to equal df within treatments minus df between subjects, not between treatments. You know that df within treatments is equal to big N minus k. df between subjects is equal to little n minus 1, so df error, right, is going to equal the quantity n minus k minus little n minus 1. How many total scores do we have? Well, it's 3 times 8 are 24 total scores. So 24 total scores minus 3 different groups. Minus the number of participants, which is 8, right? Minus 1. So that's 21 minus 7, or 14. So we have 14 degrees of freedom in the denominator. So now we can go to our F table. I like to keep mine in a little online storage called Evernote, and I've got all of my all of my statistical tables here. Here's the F table, and we're going to look up 2 and 14 degrees of freedom, and we're going to use the light face type because it's alpha 0.05. So for 2 and 14 degrees of freedom, it's F crit of 3.74. So that's the standard. 3.74. Next, calculate your test statistic. Let's go ahead and take care of the numerator first, mean square between treatments. We're going to need sums of squares between treatments. Alright, and that's equal to the sum of your t-squares divided by the n in each group minus g squared over big N. I didn't do g, but we can get it by adding up all the t's together. Right? So that's 36, 78, and 96. Alright? 36, 78, and 96. I get 210 as G. Alright. We've got our t's, so we should be able to rock and roll. That's 36 squared over 8 plus 78 squared over 8 plus 96 squared over 8 minus 210 squared over n, which is 24. Alright, let's do our calculator over here. 36 squared is 1296 over 8. 78 squared is 6084. Divide that by 8. 96 squared is 9216. Divide that by 8. And minus 210 squared, that's 44,100, and we'll divide that by 24. Okay. 1296 divided by 8 is 162. 6084 divided by 8 is 760.5, and 9216 divided by 8 is 1152. 44.1, that's the sample rate of CDs, divided by 24 is 1837.5. Alright, let's try this. We'll make that negative, then we'll just add these. 1152 plus 760.5 plus 162 gives us 237. Alright. We can go ahead and get our mean squared out of the way. Mean squared is variance, and variance is sum of squares over degrees of freedom. Sum of squares between treatments over degrees of freedom between treatments. That's 237. Right? Divided by our between treatment sums of squares, which was 2. So that gives us 118.5 for mean square between. Great. Okay, we've got our numerator. Check. We need our denominator. So to get MS error, we need SS error. And SS error is the difference between SS within treatments and SS between subjects. Not between treatments, between subjects. Let's go ahead and get SS within treatments out of the way. We've already got our sums of squares up here. That's just the sum of all the individual sums of squares for each treatment, right? So that's 30 plus 93.5 plus 30. That's easy. Ooh, look at that. 30 plus 93.5 plus 30. I get 153.5. Great. Now we need sum of squares between subjects. Sum of squares between subjects is kind of like sum of squares between treatments, except you're considering the different subjects. The fact that there are different subjects is kind of a treatment. So between treatments is the t squares over n, and between subjects are the p squares over the number of scores that go into the p totals. So it's the sum of p squared over little n, which is the number of no, I'm sorry, it's not p squared over little n. It's p squared over the number of scores that go into the p, which is k, the number of groups that you have, minus g squared, over again, big N. Alright, let's go ahead and add these up. That'll be 33 squared over 3, plus 26 squared over 3 plus 25 squared over 3 plus 34 squared over 3 plus 21 squared over 3 plus 18 squared over 3 plus 27 squared over 3 plus 26 squared over 3 minus what? Well, it's minus 1837.5 because that's the same quantity as we used in between treatments. Alright? That represents sort of the average total variability of these numbers. Average total spread of those numbers. Sort of. Let's do it. 33 squared is 1089. We'll divide that by 3 later. 26 squared, 676. 25 squared is 625. 34 squared is 1156. 21 squared is 441. 18 squared is 324. 27 squared is 729. And 26 squared is 676. Don't forget, subtract this term, 1837.5. Let's divide 1089 divided by 3, 363, 676, 225.33 with some rounding. 625 over 3 is 208 and a third. 1156 divided by 3 is 385 and a third. 441 over 3 is 147. 324 over 3 is 108. 729 over 3 is 243. Gotta continue this down here. 676 over 3 is 225 and a third. Don't forget, subtract that term. 1837.5. Let's add those up. 363, 225.33, 208. Oops. Start over. 363 and 225.33 and 208.33 and 385.33 and 147 and 108 and 243 and 225.33 is 2493.65 minus 1837.5. I get 656.15. 656.15 for some squares between subjects. That's not quite correct. Let's see where we did our error. We have 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Let's check these. See, 225, 208, 305, 147, 108, 243, 225. Alright? And that's wrong. Let's go ahead and add those up again. 225.33 and 243. And have a lot of numbers here. 147 and 385 and 208 and 225 and 363. That's much better. 1905.32. Alright. If you get an answer that doesn't make sense, go back and try it again. Subtract 1837.5, and I get 67.82. That's our between subject sums of squares. Well, we want sum of squares error. And that's, well, we've got it up here. Sum of squares within treatments, right, which was 153.5, minus sum of squares between subjects, which was 67.82. So I get 85.68. Now there's some rounding involved, so you might be a little bit off, but that's going to be our SS error. Well, in the denominator we need MS error, so let's go ahead and calculate that. MS error is variance, and variance is always sums of squares over degrees of freedom. In this case, it's SS error over DF error. From the other page, SS error was 85.68, and DF error we already calculated as 14. So, MS error is 6.12. Check that one more time. 14 degrees of freedom. 6.12. Alright. So our F ratio, right, is going to be MS between treatments divided by MS error. MS between from the other page was 118.5, right here. Divide that by our MS error, 6.12. 118.5 divided by 6.12 is 19.36. And we compare this with our critical value of 3.74 and make our final decision, which was to reject the null hypothesis. So we reject the null and conclude that there is a significant difference somewhere among these three means. But to find out what that difference is, we need to do a post hoc test, and the one that we've been working with is Tukey's HSD. It's a little bit different for the repeated measures ANOVA. It's Q, which is the studentized range statistic, times the square root of MS error, which is MS within in the independent groups ANOVA, divided by N, which is the number of subjects. To get Q, you need to use the Q table, and the Q table is right here in our trusty Evernote. And Q, you need to know the number of treatments, and the degrees of freedom for the error term. Here, the number of treatments is, you know what, I think, let's just double check and make sure that we've got the correct degrees of freedom. I believe that we do. So, with the number of treatments, here we have 3 different treatments, right? We have 14 degrees of freedom. So 4.11 is Q. Multiply that times the square root of 6.12 over N, which is 8. Divided by 8 is, so that's going to be 4.11 times the square root of 0.765. Which is 3.59. Alright. This is the honestly significant difference. The mean for the picture of the snake was 4.5. I'm just copying from the other page. The mean for the plastic toy was 9.75. Is this difference significant? 9.75 minus 4.5, that's 5.25, so yes, that's significant because 5.25 is bigger than this honestly significant difference. The mean for the rubber toy snake, which was lifelike, was 12. So is there a significant difference between these two? Right, so 12 minus 9.75, and no. So it turns out that one's not significant. But this difference is, because this difference was, and this one's even bigger. So post hoc testing revealed that the rubber lifelike snake produced a significantly greater physiological response than did the picture of the snake, and the plastic toy produced a significantly greater physiological response than did the picture of the snake, but there was no difference between the response to the plastic toy and the rubber lifelike snake. And that's all we can say about this. So I will see you next time.